Hi, everyone. We're going to talk about running large language models in Kubernetes because we live in 2025 and Gen AI is everywhere. If you have been doing Kubernetes for as long as I've been doing it, for almost 7 or 8 years, running large language models is your job guarantees, because running stuff on top of Kubernetes is the equivalent of writing COBOL code 25 years ago. This thing is going to be around for a while, so don't worry about it. All right, so we created this talk a while ago with a colleague of mine, and we called it this provocative title, Yes, You Can Run LLMs on Kubernetes. And the idea would be that if somebody reads the title, they would be like, who said you can't? And the idea is not you can't. The idea is how can you do it? And I'm not going to focus too much on actually running large language models on Kubernetes itself, but focus more on the challenges of running large language models. My name is Abdel. I'm a cloud developer advocate, as Casper said, at Google. So by show of hands, how many of you knows Kubernetes? Right, good. You're at the right conference. Awesome. How many of you have run large language models on Kubernetes? Oh, OK. If there was more hands, I would have said thank you and walk off stage. But apparently, there is none. So generative AI is evolving. It's evolving very fast. And it's evolving also in a pace and in a manner where people care more about local, open, large language models, not only cloud-hosted ones. You can't use cloud-hosted LLMs all the time. Gemini, ChatGPT, Claude, all these things are not always useful for you, either because they cannot do the things you need them to do, or for regulation reasons you cannot use them, or for latency reasons you cannot use them. And so therefore, open LLMs are the alternative. They are open because they are either open source or open weights. Open source means you have the code that used to train the model, or open weights means the weights themselves are available. And there is like a whole ecosystem of large language models, everything from Google to Ollama to Gemma to Mistral to whatever, to DeepSeek, to all of these things. The challenge is that these models are getting bigger and bigger and bigger and bigger. They're not only bigger in size, but they're also bigger in terms of the complexity of the model itself and what it can do. So before I move on, I want to spend a little bit of time talking about some basic concepts so we all understand what I'm talking about. I think large language models, everybody knows what it is, right? I'm going to be using the term inference, and I know that a lot of times when people talk about inference, they kind of mix it up with inference and serving. They say we are doing inference on the model in the sense of we're doing serving on the model, but these are completely different things. So inference is essentially the process by which a model produces results for the first time after it have been trained. Inference is the usage of the actual model. It's how the model processes the input to produce an output. Serving is the process by which you host the model. The easiest way I explain serving is I tell people, think of serving as when you have a website. A website is essentially CSS, JavaScript, and HTML. If you want to run a website, you need a web server, right? Without a web server, CSS, HTML, and JavaScript are useless. So a web server to a website is what a serving engine is to an LLM. A large language model is essentially a file, usually a text file with a bunch of gibberish code in it that you wouldn't understand. But it's not a binary. You cannot execute it. So in order to make it useful, you need to run it inside something that can take input from you as a user, translate it into how the model works, inference part, and then return the results. So that's the serving part. So a serving requires a serving engine. And today on the market, there are a couple of very popular open source serving engines. I'm going to talk about one in a bit. Accelerators, I think everybody knows what they are. If you have accelerators, you have money, GPUs, TPUs, whatever, special non-CPU type chips, essentially. Quantization. Quantization is essentially a precision characteristic of a model. A model has a quantization value, usually around 16. The higher the quantization, the more memory footprint the model needs, and the more precise it is. The lower the quantization, the less precise it is. So if you take DeepSeek, the biggest model, 675B parameters, like 675 billion parameters or something, you can run that on your M4 MacBook at home, or on your on a Mac at a lower quantization. The model is going to be less precise, but it will require less memory. Weights are the numerical value that describe the connection between the neurons. I'm going to talk about that in a bit. Context window is very important to understand. This is actually this is where people who are doing platform engineering or DevOps start to be a little bit it becomes interesting for you. Context window is essentially how many tokens a model can process at a single shot, right? That's the size of the input, essentially. And why context window is interesting is because large language models are stateless by default. If you take a large language model and you ask it one question, let's say, what's the capital of Denmark? It will reply, Copenhagen. It's Copenhagen, right? Okay, cool. And then if you start a new chat session and ask the question, how many people live in that city? For us humans, we understand that if I ask you how many people live in that city, you know that the context is Copenhagen, right? But a model across two different chat sessions wouldn't know because it's stateless, it doesn't have memory. So typically the way you make a model look smart in a chat session is each time there is a new prompt, you send the previous questions and previous answers, right? That's what we call the context. The context is essentially the full history of what you have been talking with the model. And as you are chatting with the model, the context gets bigger and bigger and bigger and bigger, right? So if you want to run a model that looks smart for a chatbot, you need a model with a very high context window. Context window is always expressed in tokens, and tokens are essentially the way models process inputs. A token could be a word, could be a number, could be a combination of letters, could be anything, right? Then the last thing is multimodality. So I want you to keep in mind these two last things because we're going to talk about them in a bit. Context window is very important. Multimodality essentially means that the model understands more than just text. It understands audio, it understands video, it understands images, right? Some of the most commonly used open source model servers are these that you see on the screen. vLLM is one of the most popular ones. It's written in Python. Hugging Face from TGI, sorry, from Hugging Face. NVIDIA has a model or a server engine called NIM. NIM is a little bit particular in the way it works because vLLM and TGI allows you to run any open model that is compatible with vLLM and TGI, while NIM is a packaged solution. It's a packaged container that contains the server engine NIM and the model. So when you're downloading a NIM from NVIDIA, you download a NIM that runs Llama 70B, blah, 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 for a very particular model, right? So what NVIDIA does is that they package the model and the server engine and they optimize them, and they ship you a ready-to-use container. It is a paid solution, by the way. Ray is an open source Python framework for doing end-to-end large language, end-to-end machine learning, including training, fine-tuning, reinforcement learning, etc. And then Ray has a Ray serve engine, which relies on vLLM under the hood. Then you have Jetstream, and Ollama is probably the one that you all know, you're familiar with if you have run it before on your laptops. There is an engineer at Google called Clayton Coleman. He made a talk about a year ago, I think, at KubeCon, where he made this statement called large language models is the new web app, with a little asterisk at the end. And we're going to see a little bit how large language models kind of similar to web apps and how they are very, very different from web apps. Just keep this in mind. So running large language models in cloud can be done in any of these three ways, right? If you go all the way on the left side of the screen, you have fully managed, fully automated solutions. If you run on cloud providers, Bedrock, Azure AI, Vertex AI, any of these solutions, fully managed, you don't see how it works. You just give them a model, they give you an URL, an endpoint, and that's it, right? You can do things your way, which is on the right side, so virtual machines, bare metal servers, low-level Linux stuff. Kubernetes gives you a little bit of that mixed between the fully managed solution, because you have the self-healing, the automation, and all the stuff that Kubernetes brings, and then the flexibility of doing things or tuning things your way. I don't think I need to spend too much time on this, but why do we want to run large language models on Kubernetes? For many reasons. The automation part is obviously scalability. Kubernetes started about 2-3 years ago actually adding more capabilities for large language models. One of them is device management for managing GPUs. There is something called device plugin in Kubernetes, which allows you to claim GPUs using Kubernetes primitives, so using YAML files. There is another API that became GA actually very recently called DRA, Dynamic Resource Allocation, which allows you to claim GPUs, claim accelerators for large language models or for machine learning models, and multi-cloud, so you can run it anywhere, right? So why would you want to run large language models locally? Well, many reasons. Regulation would be one of them. You run on a regulated industry that doesn't allow you to use cloud. That would be the easiest one. Latency, you want the application and the large language models to be as close to each other as possible. Special use cases, in a case where that large language model, which is hosted by a cloud provider, doesn't work for you, so you need to fine-tune it, which means you need to start from a large language model, tune it specifically for your use case, and then run the tuned version. Privacy is another one. You simply don't trust the cloud. Cost would be another one. Most of cloud-hosted large language models charge you for input and output tokens, and those can go out of hand very, very quickly, especially if your developers don't know what they're doing. So you want to control cost, or you want to have predictable cost, in which case you're going to buy hardware upfront and then run the large language model, or any combination of all these reasons, right? So let me show you real quick how that could look like. I mean, if you are a bit like me, and you're a big fan of YAML, because let's face it, somebody who does Kubernetes is just a YAML engineer at heart. This is how a deployment could look like. This is a running vLLM. So nothing that different. Here we have the container. One thing you will notice is that we're running here vLLM OpenAI. So OpenAI came up with an API spec a few years ago called the OpenAI API spec. And that API spec basically standardizes the way the model or the API gets presented to you as a user. So the way you would call the model will be standard, regardless which model is running behind the scene. This particular container that I'm using here is vLLM plus the OpenAPI spec activated on it, right? I have my resource requests. One thing you will notice here is this. This is part of what Kubernetes offers out of the box, device management. You can actually request a GPU. So here I'm saying I want one GPU. I have a bunch of arguments to start my container. One of them is which model I want to run, how many tensor parallel size, so how many GPUs I have. In this case, I just have one. And then where does vLLM start? Just one thing to keep in mind quickly, those are arguments to vLLM itself. They are not arguments to the model. They're arguments to just the container itself, right? So in this particular case, what's going to happen is vLLM is going to start, and then it's going to download the model from from Hugging Face, not OpenFace, because I passed the -- model flag, right? Also, I have here a token. This is a Hugging Face token. That's how it will, authenticate to Hugging Face and download the actual model. And here I say I want a node selector. My cluster that I'm running in this particular case has a couple of nodes that has GPUs, a couple of nodes that doesn't have GPUs. To make sure my workload ends up on a node with GPU, I just have to add a node selector. You could also do taints and tolerations. If you're running on top of a cloud provider that offers a fully managed Kubernetes solution, like Autopilot and GKE, or I forgot the other one on AWS. They have their own ways to allow you to say, I want this particular type of nodes to be provisioned for me. So this will run the model for me. So if I go and look it up, I just have a pod running. One thing I want to do with you here is I want to quickly check the logs of that thing, and I'm gonna explain to you why in a second. So let's see how this container started a while ago, right? So let's go back in the logs and see how it started. So I have my vLLM starting. This is the first log item of the vLLM container. Keep in mind this value here. We're going to talk about it, 518, right? Then it did a bunch of things, blah, blah, blah. And then this is where it started downloading the actual model. So this is downloading the model from Hugging Face and loading the model into the GPU and doing a bunch of things. And then where it says it's ready, it's basically there, here. This is where vLLM says, I'm ready to serve traffic. So it took about roughly 2 minutes between the model, the container actually starting and the application being ready to serve traffic. One thing to keep in mind here is I'm doing something a little bit stupid. I'm not using any sort of like health checks, liveness probes, or readiness probes. So in this particular case, when my container starts, Kubernetes flags it as ready, but if I try to talk to it, it's going to return nothing for a while, right? So because the model is not loaded yet. So if you're going to run large language models on Kubernetes, one of the recommendations is obviously to use something like health check probes. These are the health check readiness probes and liveness probes for vLLM itself. So vLLM has a /health endpoint, and then it will return 200 on that when the model is ready to be to serve traffic. So now, if I go and port forward my container here, and then run another curl command somewhere like that, I'm going to show you something real quick here. So I'm going to run a curl on my local host, obviously, /v1/stat/completions, that's the OpenAI spec. That's essentially how OpenAI defines its endpoints. So the /completion is the actual endpoint where the model is. Notice here that I have to pass the model ID as part of my body of the request in the JSON payload. And I have to pass a bunch of messages. My messages are an array, which means I can actually append them. So if you're trying to create a real chatbot, you will basically append the new prompt to the array each time the user types a prompt in the application, right? So you will send a very long JSON file. And that essentially is the context window that I've been talking about, that array of messages. And the reason why here it says role user is because most models also support something called system prompts. So system prompts are the instructions that you as a developer will send to the model to tell it to behave a certain way. If you want to limit or make the model focus on a very specific problem, you can send a system prompt to tell the model, you are an accounting expert. Please answer these questions, blah, blah, blah. And then you can tell it very specific instructions. So you don't want those to be sent by the actual user. You send them as part of the application system prompts back to the model. So if I run this, it's going to return an answer about why is the sky blue. It's going to take a little bit of time because this is a very, very basic deployment with no optimizations whatsoever. And I'm going to talk about what those optimizations are in a bit. So now I have my return and my prompt, very, very, very easy. So this is like the most basic bare bone way of running a model on Kubernetes. A regular deployment, random model, and that's it. In case in this particular case, I just have one pod, right? So it's pretty basic. But let's say I start suddenly to have more traffic on my application. So the obvious response is I want to scale it out. I want to add more replicas of my pod so I can handle more traffic. It's not that simple. You remember I started by saying that large language models are the new web applications? Now we're going to talk about why they are not the new web applications. Well, one of the most obvious ones is the fact that they require GPUs. Web applications doesn't require GPUs, right? Obviously. But the other way is the fact that the model servers are actually pretty big. So this is a benchmark I did on a bunch of these very popular model servers. You can see the vLLM OpenAI is the second one. It's about 5 gigabytes in size. When Kubernetes started 10 or 11 years ago, and containers probably 12 years ago, this entire time, everybody was just trying to optimize the size of a container to make it as small as possible. And now OpenAI is just Gen AI is just blowing that out of proportion. You can see, if you go all the way down to Puddle, it's 14 gigabytes. What you see on the last column is the average image pull time. So if we take the example that I showed earlier of running Gemma with vLLM, between vLLM starting and then the model being ready to serve traffic, it takes about 2 minutes, right? Then it takes another 2 minutes, roughly, 155, to pull the model. So essentially, between the time you do a kubectl apply on a vLLM with a Gemma 1B, which is a very small model, on Kubernetes, it takes roughly 4 minutes for the container to be ready to serve traffic. So you can imagine in a scale-out scenario, this would be super slow, right? If you have a horizontal pod autoscaler, targeting that pod, looking at certain metrics, and then scaling up the pod horizontally when there is more traffic, it will just take more time, or it will take time, essentially, for your container or for your models to scale out. And things get a little bit more complicated as you are going up in the size of the model themselves. So this is a little table that shows a couple of the open source models on the left side. So we have Gemma, Llama, Falcon, Flan, I think, and DeepSeek. And you see the model variance, so that's the number of billion parameters. And then you see the precision, the quantization. I want to draw your attention to the last lane. A DeepSeek 685 billion parameters, so that's the largest variance DeepSeek model that exists today, at a full precision requires 1,370 gigabytes of GPU memory. 1.3 terabytes of GPU memory, right? Today, there are no GPUs in the market, I dare you to challenge me on this, that has that much memory. The biggest GPU you can get on the market today is an H200, I believe, which has 80 gigabytes, right? So we can do a little math question, which is divide 1,370 by 80 to figure out how many GPUs we need. We're going to need 17. So to run DeepSeek 685 billion parameters at full precision, you need 17 H200 GPUs, right? And I don't know how many of you are as old as me, but if you have done any sort of hardware work in the past, you can't fit 17 GPUs on a single server. There is a physical limitation to the number of PCI Express ports available on a single server, which means to run DeepSeek higher precision, you need more than just one node. You probably need two, because most probably you're going to have a limitation of 8 PCI Express ports per node, which means you need 2 nodes to run a DeepSeek model, the largest variant at the very highest precision. And that creates a bunch of challenges. One of them is, how do we do multi-host serving? What I showed earlier is a single node, single GPU. So that's one Gemma, one B running on a single node on a single GPU, right? But you might actually run into situations where you might do single node multi-GPU. So the same model is loaded on multiple GPUs on the same exact node, which is a pretty easy way, but it's relatively. Most serving engines like vLLM already knows how to do that. But splitting a model across multiple nodes create another host of problems, which I'm going to touch on in a bit. Before I move on, another way in which large language models are not like web applications is the way traffic or network traffic looks on those particular large language models. Web applications tend to have uniform small requests that are very fast, right? Microservices mostly have these kind of characteristics. A lot of requests, very small, very fast. Large language model could have requests of variant sizes. It could be a very small prompt, hi, how are you today? Or it could be a book to summarize, right? It could be a video, it could be an audio, it could be any sort of this kind of variations in how the request looks like, which means that the request load would not be distributed evenly. And if you use a regular load balancer, an HTTP load balancer, you might end up with what you see on the right side, which is instances that have a lot of load and instances that doesn't have a lot of load. So I'm gonna skip this to this. So examples of how those kind of network traffic profiles can be different are things like a code assistant. A code assistant will have very, very large inputs, because as part of using a code assistant large language model, you are sending your entire code base and then a question, right? So the input is very large. A chatbot might also have the same characteristic, very large requests, especially as the user is speaking to the model and then asking follow-up questions. So the more questions they're asking, the bigger and bigger and bigger and bigger that input is, right? A generative AI media, so a large language model that can generate text or video or audio, can also have very large inputs, either a video or like a picture or something like that. Or sometimes you just have small prompts. So if you're familiar with this API in Kubernetes called the Gateway API, I hope it's 2025. I hope everybody knows what the Gateway API at this point is. The Gateway API was created to replace Ingress in a way. And then a few years ago, a new extension was introduced to the Gateway API called the inference extension. The inference extension is meant specifically to solve the problem of uniform or ununiform or not uniform network or prompt inputs across instances. So how does it solve it? By introducing 2 new objects. One is called an inference pool, and one is called an inference objective. So an inference pool is just a parameter or like an object that tracks multiple model servers. So you would have multiple Gemma tree, multiple Llama, multiple Falcon running, and then you group them inside an inference pool, kind of like a node pool in Kubernetes. And then an inference objective is essentially the way you define policies. That's how you tell the inference extension, I want to prioritize this traffic versus this other traffic, or I want to route traffic from this particular point to this particular point. An example here would be body-based routing. You remember here when I said part of the inputs for OpenAI, you have to specify the model in the JSON payload. So the question is, if I have multiple types of models with multiple different models, and I want to expose them behind a single load balancer, how do I make it sure that when the request comes to the load balancer knows where to route the request based on the model ID? The Gateway API itself, out of the box, does not know how to process the body of the request. The Gateway API can only look at the request path, but it cannot read the request body, the payload. So that's why the inference extension added something called the endpoint picker extension, or endpoint picker, EPP. And the endpoint picker is a component that when the request gets to the gateway will send the request to the endpoint picker. The endpoint picker will pull the body of the request, pull the model ID, and then returns back to the gateway API which endpoint to forward the traffic to, depending on the body of the request. And that's essentially where you will also define some policies. You can also define prioritization policies. You can say, if requests are coming from my chatbot application, I want to prioritize this versus requests coming for another type of application, right? So the inference extension extends the gateway API to make it large language model aware, in a way. And then last but not least, I'm going to touch on is something called LLMD. Doesn't stand for anything, it's just LLMD. It's an open source project. It's a collaboration between Google, Red Hat, ByteDance, and NVIDIA. And what it is, it's essentially taking the inference extension in the gateway API, taking vLLM as a core serving engine, and creating well-defined configurations that make sure that when we run a large language model on Kubernetes, we run it in an optimized manner. So LLMD defined this thing called well-lit paths. So a well-lit path is an opinionated way of deploying things. And as of now, it has two well-lit paths, something called intelligent inference scheduling. This essentially deploys vLLM behind the inference extension with the gateway API, and then introduces a new endpoint picker. So it's a revised version of this component here called the endpoint picker, which intelligently knows how to schedule the requests based on multiple characteristics. One of them is the body of the request, so the payload of the request, but another one is how busy are the models in the backend are. So the endpoint picker that the LLMD introduced is actually able to read metrics from vLLM to know how busy a particular pod is. And by busy, the way we define busy in a large language model sense is not CPU and memory utilization. It's GPU utilization. It's queue depth. So a lot of these large language model serving engines, they will queue or they will batch the requests. So as the requests are coming, they will group them in a batch and then they will process them in one go. So that creates a queue, and vLLM can expose a metric that tells you how big the queue is, and then the inference extension in LLMD can read the size of that queue and decides to forward the request to one pod versus another, depending on the size of the queue. It also gives you the flexibility to add some policies, like say, send traffic. For example, let's say if you want to skip any intelligent processing for small prompts, so if the prompt is like, hi, how are you? I can define a policy that says, if my prompt size is less than a certain number of tokens, just like process it right away, don't do any sort of smart scheduling. But if it's bigger than a certain size, then you do some sort of smart scheduling. So that's LLMD. The second one is it defines something called desegregated serving. I don't want to go too much into the details here because I don't have time, but desegregated serving is essentially a process by which you split the inference process of a large language model across two steps, a prefill and a decode. Very quickly and very loosely speaking, prefill is the process by which you take a prompt, you read it, and then you generate the tokens, and then you put them in the GPU memory. Decode is the process by which you generate the actual tokens. So prefill processes the input, decode generates the output, right? So if you, like what the example I showed earlier, I'm doing prefill and decode on the same instance. LLMD will split or has a capability to split these two processes across two different instances. You will have pods that are specifically dedicated to do prefill and pods that are specifically to do decode. So the pods that are specifically doing prefill will generate the tokens, load them into a cache, transfer that cache to the pod that can do decode, and the pod that can do decode generate the tokens. I've done a 3 hours talk about this yesterday in Belgium, so I'm not going to go into the details here. I'm happy to answer the questions later, but just LLMD has these capabilities: intelligent scheduling, prefill, decode, desegregated serving. There's actually a white paper about this if you want to read it. This is kind of roughly how the architecture of LLMD itself looks like. It uses the inference gateway, which is envoy-based. It has the inference pool in the back, so that's where your pods will be running. And then on the side, it has the inference scheduler, so that's the intelligent components which routes traffic to a specific instance based on utilization, how busy it is, the queue depth, the utilization of the cache, etc., etc. Very quickly, couple of things. We talked about single host serving, single host multi-accelerator serving, multi-host multiple accelerator serving, the example I showed earlier of DeepSeek 685B parameters, which require 17 GPUs. There is an API in Kubernetes called LWS, leader worker set, which allows you to actually do that. So leader worker set is the API in Kubernetes that allows you to do multi-host serving. So running a model across multiple hosts, right? And it looks a little bit like Kubernetes in the sense that it has a leader and a set of workers. The workers themselves are stateful sets, and the leader is a component that is tracking where the workers are and where the neural network is, right? And so leader worker set is how you would do multi-host serving on Kubernetes. So I think this is my last slide, hopefully. Yes. I want to just recap everything I've been talking about. Running large language models on Kubernetes is similar to how you would run a web application on Kubernetes because it's all YAML based. But the challenges you're going to have to solve are very, very different. And all the layers of optimization that we know for web applications, caching, horizontal scaling, etc., doesn't really necessarily work for large language models. Just taking a large language model which is slow, running it on top of a faster GPU is not going to give you better results. You will have to think about it as multiple layers, including the accelerators you're using, the serving platform, the large language model itself, the underlying storage, etc., etc. So this is the end of my talk. We have this QR code that will take you to a GitHub repository. We wrote a demo that basically runs like 10 large language models on top of Kubernetes and gives you a single web interface to talk to all of them at the same time if you want to give it a try. If you have deep pockets and enough GPUs to burn, this is a great demo to run, actually. And with that, I'm running out of time, right? All right, I'm going to stop here. This is my QR code to my link tree if you want to connect with me. Thank you so much. I hope this was useful.
Thank you so much.